Yes, thanks everyone for attending today's session and my talk. I'm Robert Daniluk. I'm a PhD student at the University of Cambridge, supervised by Herb Yasak, and working with Walid Al-Salami and William Anderson from Upton Chemical. The title of my work is Accounting for Mechanical Properties of Zddp Tribofilms in Continuum-based wear simulations. So to start with, let's talk a bit what is Zddp at all. So it is the most commonly used anti-wear additive. So essentially, it is a chemical that we put into lubricating oils that when it comes into contact with steel surfaces or maybe some other materials as well, but we usually consider steel, it forms protected tribofilms. And then when sliding and rubbing of surfaces occurs, the tribofilm is being worn out instead of the underlying steel. And that's the way in which it basically prevents wear on surfaces. The tribofilms themselves are of thickness of about 50 to 200 nanometers. And here on the right side, in the right image, you can see a good scan, basically a real scan of one ZDP covered surface. And you can see that the surface itself is quite patchy. The tribofilm itself is quite patchy and bumpy. So in general, this project, this is part of a bigger project that is dealing with trying to simulate the whole, let's say, life cycle of the tribofilms. So basically how they grow on surfaces, how they protect surfaces from wear. And to be able to model this, one of the important components is to be able to model the mechanical properties of the films. So we are mostly interested in the hardness and the elastic modulus of the films. And essentially, they both reduce in value as the tribofilm grows. So the tribofilms have a lower value than the underlying steel of both hardness and elastic modulus. And also, usually, depending on the properties of the film, they reduce in value as the tribofilm is bigger and bigger. The reduction of hardness affects the plastic deformation rate because it's connected with the yielding deformation, and it also affects the surface removal rate. You can basically refer to Mr. Baltinet's presentation 2 presentations ago to see how hardness refers to or correlates with wear. And also, as the elastic modulus diminishes, the maximums of contact pressures in the system become smaller. So basically, it is something like putting a cushion or a pillow in your contact between the two surfaces. So that's how the elastic modulus reduction affects the system. So let's just look at some of the values of the hardness and elastic modulus of the films themselves. If you look at elastic modulus, steel usually has, maybe depending on the steel, but let's say usually has elastic modulus of about 200 gigapascals. And if you look at these results, they say that this for the film is something like 15, maybe 40 gigapascals, maybe a bit more, depending on the measurement we look at. And for hardness, hardness for steel is, again, depending on the type of steel, etc., can be up to 5-7 gigapascals. And here for the tribofilm, we see that it is about 1 to maybe sometimes up to 3 gigapascals. So, okay, they are definitely lower value. The problem is, in general, simulating this is not an easy problem in one part because there are various scales involved in the problem. So if you look at the components, they are of centimeter scale, maybe meter. I'm talking about the actual mechanical components, the engineering components. If you look at the roughness scale of the steel, it is in micrometers approximately, and the tribofilm itself is in nanometers. And that's why, even though the tribofilm has a quite lower hardness and elastic modulus than the steel, the question is how much this affects the actual contact mechanics and the wear. So we want to be able to answer this question and also to exactly quantify it and get a model that we can actually plug into proper Zddp dynamic growth and anti-wear model, etc. So just to look at the contact mechanics model, so it is essentially the same one used by Mr. Baltinen, so I don't have to go into too much detail. So let's just say it's a mixed mode lubricant contact model that's able to solve for contact situations from the hydrodynamic thick film regime all throughout to the boundary lubrication regime. So this is what we are aiming to use in the total Zddp dynamic Zddp model of growth and removal. And it's also important to note here that it is essentially two-dimensional. Conservation equations are solved in 2D, but we are also tracking heights of the surfaces along the 2D domain. So this gives us this additional, let's say, half dimension. One key assumption is that on both sides of the contact, infinite half spaces are present of the same isotropic material, which means that basically we plug in one singular scalar value for the elastic modulus, which is problematic for us because the reality is not like this. The tribofilms are highly patchy, the elastic modulus can vary a lot, and hardness along the tribofilms, etc. But this is not the deal. However, this is the most commonly used model in rough surface wear simulation because it is the best compromise currently of accuracy and computational efficiency. So let's see if we can go around this issue somehow. Looking at some previous researchers, some people said, okay, I'll just assume that the elastic modulus of the tribofilm is the same as the elastic modulus of the substrate, which is steel. Some people said, okay, I'll go around the domain. This is the second basically assumption. And I'll average the elastic modulus that I find all over the domain and simply plug in that one value. Another solution used by people is a layered quantum mechanics model, which allows for layers of different materials in the normal direction of the contact, but with a uniform thickness of the layers. So this is not ideal because Zddp tribofilms are very patchy, and this is an assumption we don't really like in this case. I'm talking about the uniform thickness of the layers. Now, if we also look at hardness and plasticity modeling, this is quite closely linked because in the quantum mechanics model, hardness is basically determining the plastic deformation. So some people simply said, okay, we're not going to account for plastic deformation, which can be okay depending on contact parameters, contact properties. Sometimes the contact pressures are simply low enough, but we want to be able to cover more cases than that. In 2012, Anderson et al. Published a plastic yielding algorithm that was used by multiple other researchers. And in this work, it was also used in a slightly modified form. And I'll get to that a bit later, basically. To talk about my proposed elastic modulus model. So the idea is inspired by equivalent resistances in electric circuits or equivalent thermal resistances in thermal circuits, which is very similar ideas to one another. Or equivalent elastic modulus of an axially loaded beam consisting of axially distributed segments with varying elastic moduli. To give you a better idea of what I'm talking about, if we have a case with three different segments with three different, let's say, lengths and elastic moduli, etc., we can use this formula to calculate the equivalent elastic modulus of the whole total segment, and that's how we can calculate the deformations, in this case, if it's actually loaded, etc. In a realistic 3D context scenario, this is not as simple because, number one, there's a radial component to the solution. It's 3D after all, not just 1D. Number two, there's also there's an importance to the depth in the solution. So we can't just use this approximation, but there is an equivalency here to what I'm proposing. So what I'm proposing to do is, when we define the surface geometry of the surfaces in contact, let us use a bit of the substrate material to represent the effect that the existence of the tribofilm has on elastic behavior and contact mechanics. So to give you maybe a better explanation of this, let's consider three scenarios. One is, what if the tribofilm had the same elastic modulus as the substrate? We can simply say, okay, the surface is the substrate level. So these are basically surface levels plus the tribofilm level. And if we assume that the tribofilm has the same elasticity, we just plug in the elasticity of steel and we're good to go. What if, this is the second scenario, what if the tribofilm would be mechanically negligible in a sense that it has a zero elastic modulus? In that case, the elastic model is simply not going to see it. And then we can say that the total height of the surface is simply the height of the substrate and just use the steel elastic modulus. And when we combine these two cases, the final proposed solution is to use this term, which has the ratio of the elastic modulus of the tribofilm and the steel. So we're accounting for this here. And we're using a calibration parameter n. And in general, this whole term has to be between 0 and 1 to respect that we have to be in between these two scenarios. So right now it sounds like a bit of black magic, but we have designed validation cases and seen how this performs. And yeah, so this is visualized here. So we have 3 different test geometries. In all the 3 cases, the gray surface, the gray volume is steel. The blue-ish surface is a tribofilm on top of steel, and the geometry used here is quite representative of actual scales that are in tribofilm contact. And here the 2 reddish surfaces, flat surfaces, are pressing, they're perfectly rigid and they're pressing against the tribofilm. And then in the 3rd case, we took both of these 2 tribofilm surfaces and we are pressing them against each other and seeing what happens. As a reference in our validation, we are using a solution achieved using solids for foam, running full 3D simulations with a non-uniform elastic modulus material model implemented. So this is these are results that we can be quite confident in, if we can be confident in anything, basically. So we can look at some results. So first we looked at the solution we get using the spheres geometry that was on the left here in the previous slide. So the full blue solid line is the result using solids for foam and a full 3D film, fully resolved film. The different dash surfaces with different colors, they are what we get when we vary the n exponent, which is basically a calibration parameter. And here, doing this parametric sweep in the spheres case, we realized that n equals 0.25 gave us a very good match with the solid line. So, sorry, I forgot to mention. So this, along the x line, we have the average contact pressure that is increasing as we press the surfaces against each other. And on the y axis, we have maximum contact pressure in the domain. And here we have contact area that is also increasing, of course, as we increase the load between the surfaces. So, okay, we saw that here the n.25 gave us a very good result. Then we saw, okay, how it's going to work with the other 2 cases, and it still works pretty well. So this is looking at the match between the solid blue line and the dashed blue line. So, okay, let's also see the time evolution. Sorry, so this is when we plot the solution of contact pressure along these 2 lines, so the green and red lines, and we look at how the evolution of the solution looks if we plot it there. And again, the dashed line is our model, and the solid line is a full 3D solids for foam simulation. And we can see that even at lower loads, for example, the blue line, or at higher loads, for example, the yellow line, we get a very good match with the reference solution. Okay, now that we have a model we're happy with, let us try to see how it compares against some of the other previously discussed ones developed by previous researchers. So this is a simulation case where we have a steel ball pressing against a steel flat surface. The steel ball has a wavy tribofilm, and the steel flat surface has a wavy tribofilm, however, in 2 directions. And these are the results we get depending on the modeling assumption we use. So the first one is if we assume that the tribofilm is has the same elastic modulus as the steel. So this is the case in which we get the highest maximums of contact pressure. As you can see, this most intense yellow color. Then this is basically a proposed solution. This is our model with n equals 0.25. So we see the difference here is not massive, but it is of the order of 10 to 15% for the maximum contact pressure. Another interesting one is if we look at the solution, which is basically if we do domain averaging of the elastic modulus, and we can see that this produced a basically very poor result in this case. This is if we assume that the tribofilm is mechanically negligible, as discussed previously in one of the scenarios. And this is if we assume that there is a tribofilm, but it has a uniform thickness that is the average calculated from the previous tribofilm geometry. So that is it regarding elastic modulus. Regarding the hardness and plastic deformation, So once we have a contact solution, right, we have a contact pressure field in the domain. And if we go along the domain, if you look at each phase, in each phase, depending on the contact pressure in the phase, 3 states are possible regarding plastic deformation. So one is that there is no plastic deformation in either of the tribofilms, top or bottom, which means that the contact pressure is low enough that it hasn't deformed anything. The second scenario is that there is plastic deformation in only one of the tribofilms, which means that contact pressure is high enough to deform one of the surfaces, but the other one is too hard or has a too high yield stress threshold. And the third case is if the contact pressure is high enough to have deformed both of the tribofilms. Now, Anderson et al. That I mentioned before, the algorithm published in 2012 used similar 3 scenarios, not completely the same, but similar. And then they they use a different formula to calculate the deformation depending on the 3 cases. I devised an equation that could be used for any of the 3 cases, and it can basically work for any of them, which is basically dependence of the plastic deformation on the contact pressure and other parameters that define basically the hardness profile of the tribofilm and the overall tribofilm thickness, etc. Another thing to note is that if we get a contact solution, if you apply this plastic deformation, this could significantly change the solution, which means that we have a coupled problem essentially. And to accommodate for this, we are applying an iterative procedure where we iteratively apply a little bit of new plastic deformation at one time, and then we recalculate the contact mechanics, and then we again reapply a little bit, and that's how we get to convergent behavior when we can't calculate any more new plastic deformation. So this is a convergence of that model. And then once we have this plastic deformation, we can calculate the final surface level, now referring to the previous elastic modulus model, as the sum of the substrate and then sum of the tribofilm with deformations, and then with the tribofilm elasticity correction factor. We can look at how this affects our results. So essentially, here on the left side, we see a lower load. On the right side, we see a higher load. And on the top is with plastic deformation, and on the bottom is without plastic deformation. And we see that these results at the bottom have a higher, more intense yellow, which basically tells us that there is a higher pressure, and this is of the order of 10 to 20%. Now, before I conclude, I just also want to know that these differences, both with the elastic modulus and the hardness that we get in the contact pressure solution that are of the order of 10 to 20%, can be very significant when modeling Zddp tribofilms, because the growth terms that are used to model growth of the tribofilms have an exponential dependence on the contact pressure and or shear stress, so the 10 to 20% difference can be quite significant, actually, when we try to model Zddp growth. So to conclude, we discussed the importance and challenges of accounting for the mechanical properties of Zddp tribofilms in continuum mechanics simulations. We looked at existing approaches and proposed new ones to model the elastic modulus and hardness with the resulting plastic deformations. We are happy with their simulation results. We consider them promising. And for future work, further validation is always good, of course. Maybe improving quantum mechanics capabilities. Maybe in the future, 3D simulation will be feasible. Maybe a data-based approach ultimately would be good for the quantum mechanics model, and etc. And this model will be used and is being used right now in continuum-based simulations of Zddp tribofilm dynamics and wear prevention. Thank you for your attention, and please do ask if you have any questions.
Okay, let's move to the questions. Did you have some questions from the floor? Yeah, maybe I have one. Can you hear me?
Mm-hmm. Yes, I can. Thank you.
Yeah, because I'm quite not familiar with this subject, but I see a lot of numerical results using your method. But is there any like experimental data that to validate your results?
That's a very, very good question. So I can answer this if we look at the general model of Zddp growth and anti-wear behavior. And here there are experimental results where basically people can measure the thickness of the films that is evolving throughout time, etc., etc. In this case, these things are very small. They are of nanometer scale, micrometer scale. They are in contact. It's just simply hard to measure. So in this case, it was easier to use basically simulation results that we can trust for reference. But those methods have sometimes been calibrated compared against some experimental results. So for example, you have some experimental results where people looked at contact of the order of, let's say, micrometers, and then numerical contact mechanics methods have been validated against that. And then let's say we're using that method that has been validated against that, and comparing it to a solids for foam simulation is kind of the best we can do with this level of detail and scale. Yeah, it's hard to get experiments with such tiny things for detailed contact pressure scans, etc.
Okay,
But thank you for the question.
Yeah, so I see you have compared your results with the solid for foam, right?
Yeah. Well, the thing is, let's say if I were able to use solids for foam for my ultimate model of Zddp growth and anti-wear behavior, I would be very happy. I would be perfect. But the thing is that this model is simply not as good, but it's much more computationally efficient, and that's why it's possible to use it. And solids for foam, for example, a full 3D simulation would be unfeasible because when you're trying to simulate this, the surfaces grow and the meshing would be horrible, and the solution would be very slow, etc. So yeah, that's why we are quite happy if we are close to solids for foam, a full 3D solution.
Yeah. Okay. Thank you very much.